Welcome back, everyone. Today we're going to talk about inverse functions, which, as I discussed in the last video on bijections, is basically when you take a bijection and turn it around. Alrighty, so here's the official definition. So if we start with a function, f from a to b, that's a bijection, then we define the inverse function, and we're going to denote it with an f to the minus 1, that's standing for inverse function. It's going to go from b to a instead of a to b, so that is to say the inverse function exchanges the domain and the codomain. And we're going to define it on a particular element, say little b of big B, to be the unique element of a, such that f, the original function, of little a is equal to b. Now I want to talk briefly about this word, the unique element, so why unique? And so when it says there's a unique element with this property, this again is the mathy way of saying there's exactly one. We talked a little bit about the word unique when we talked about the division algorithm. So I'm just going to emphasize, what is this part of the definition saying? It's saying there is exactly one A with this property. And so that raises two questions. The first question is, why is it important that there be a unique element with this property? And the second question is, why is there a unique element with this property? So let's start with why it's important. So I'm trying here to define a function f inverse from my function f. And so I'm trying to define what f inverse of some hypothetical element is going to be, and I give a description. Now, one possibility is that exactly one thing meets that description. Great. But there are two other possibilities that are both bad. One is that no element meets that description. So maybe, hypothetically, in some alternate universe, there's no little a, such that f of little a is equal to b. Well, then what's wrong? Well, then I failed to define a function, right? Because the fact that this is a function with domain b means that it has to be defined for every element of b. And so if when I describe this element with this property, it turns out that there are in fact no elements with that property, I've not defined a function, and so I have failed at my goal. Another possibility is that there's more than one element with this property. And why is that bad? And that's slightly more subtle, but the problem with that is if there's more than one element with this property, then I have to choose which of them I'm going to define to be f inverse of b. And what that means is that my function f inverse might be different from your function f inverse, because we might make different choices. And the mathy word for what's wrong with that is well-defined, or more precisely, not well-defined. So something is only well-defined if from the definition alone you've unambiguously described the object that you're talking about. And so if you've left choices in for the person who's doing it to make, such as, hey, which of these many elements do I want f inverse of b to be? Well, then it's not going to result in something well-defined. But the definition is actually asserting that neither of those problem scenarios, the situation where it's describing 0 elements, or the situation where it's describing 2 or more elements, the definition is asserting neither of those two things ever happens. It's telling you there's always exactly one, and so there's always one thing, so there's always something to define this to be, and you never have any choices to make. It's going to be exactly the one thing with that property. Now, this is pretty common for mathematicians to do when they're writing down definitions, but it's actually a little weird because this piece I've underlined here is really asserting something, whereas definitions are generally, at least in the purest form, not supposed to make claims. But this is really sort of a theorem in its own way to say that there is such a unique element, given the functions of bijection. And so there's sort of like a hidden proposition or theorem inside this definition. And this hidden theorem / proposition, what it says is this. So, that brings us to the second question. Why is this statement true? So, note here the quantifier is there exists a unique. And so we have not proven there exists a unique quantifier statement before. So I'll go over, as I do this proof, the general structure of that. And so we're going to do this in two pieces. First, we're going to address just the there exists part. So I'm going to suppose that f from A to B is a bijection, and that little b is an element of big B. So why does there exist a little a in big A such that f of little a is equal to b? Pause for a moment and think about this, because you really should be able to articulate in one very short sentence why that's true. And the very short sentence is because f is onto. Why is f onto? F is onto because it's a bijection, and a bijection is both one-to-one and onto. And what does f is onto mean? It means for every element of the codomain, there's an element of the domain that maps to it. So that handles the existence part of the proof. Namely, the existence part of the proof is literally the definition of onto. Part 2 of the proof, though, because it's not good enough that there exists one, I want to show that there exists a unique one. So part 2 is to talk about uniqueness. And so this is the part we have not done before. But the model for proving that something is unique is to assume that you have two of them and then show that the two things are equal. And so I guess I'm going to assume that those two things are called x and y. And so again, the structure here is a little weird. I'm trying to show there's not more than one of these things. So I've assumed there's two of them. But what is it I want to show about the two of them? I want to show they're actually the same. Note, this isn't a proof by contradiction. I'm not assuming that x and y are different. I'm just assuming that x and y both have this property. And so if just the fact that x and y both have this property implies that they're equal, together with the fact that at least one thing has this property, that will tell me that in fact there is a unique thing with this property. So I've supposed that f of x is b and f of y is b, and I've noted for you that x and y both have to be an a for this to even make sense. And so, thus, what does that tell me? Well, that tells me that f of x equals f of y. Now, this should raise some alerts in your mind. Where have I seen that before? And the place you've seen this before is in the definition of one-to-one. Namely, what does it mean for a function to be one-to-one? It means that if two inputs map to the same output, the two inputs were actually the same. And so remember, f is a bijection, so f is one-to-one. And so since f is one-to-one, this tells me that x is equal to y. But remember, that's what I wanted in order to show uniqueness. I wanted to show that if there were two elements with this property, they were the same element. And so together, that gets me existence and uniqueness, and so I have completed the proof of this hidden proposition that was smuggled inside the definition of inverse function. So I'll summarize the main takeaway from what we just did. The main takeaway from what we just did is that inverse functions do not make sense for anything except bijections. Okay, so let's talk through some examples of inverse functions. So to make an inverse function, I have to start with a bijection. And so the bijection I'm going to start with is my first example here. I'm going to call exp. Okay, and you might recall exp. This is the function that goes from the reals to the positive reals, that takes some real number x and maps it to e to the x. And this function is a bijection. Now, just to recall, why is this function a bijection? And I want to think about this in as calculus-y a way as possible. So here's a rough graph of e to the x. And so when I say that this function is one-to-one, I'm saying that no two inputs give the same output. You might recall we said previously that if a function is increasing, it's automatically one-to-one. That's definitely true here. Why is it onto? Well, it's onto because I get every positive real number as an output. That is, any point I pick on the positive y-axis, there's some input that maps to that. Notice I needed to put the positive reals here, or it would not have been a bijection. If I'd just written r to r, then it would have failed to be onto, and then we wouldn't be able to do what we're about to do. But because this function is a bijection, it has an inverse. And so this x inverse function, what is its domain? Well, remember, taking an inverse function flips the domain and codomain. And thus, the function x inverse, its domain is the positive real numbers, and its codomain is the real numbers. And so let's try and understand what it is that this function is doing. So let's try and figure out what x inverse of, say, 1 is. 1's a real number, why not? So let's look at this next to our definition. So x inverse of 1 is supposed to be the unique element of A, which remember is R here. It's supposed to be the unique element of R such that exp of A is 1. Or, if you want, that's just saying e to the A is equal to 1. So it probably won't take you too long to figure out what this A is. Namely, this A has to be 0, right? The only power I can raise e to and get 1 is the 0th power. And so what we've learned here is that x inverse of 1 is 0. And so why is x inverse of 1 0? That's because exp of 0 is 1. So we alluded to this last time. If I start with r here and r plus here, and I look at the function exp that goes in this direction, it takes 0 to 1, and so there's an arrow, among many other arrows, that goes that direction. But what an inverse function does is to just literally reverse all the arrows. So now instead of being an arrow from 0 to 1 on the original function exp, on the function exp inverse, it goes the other way, and I just erase the arrowhead at this end and stick an arrowhead at that end. And so it now takes 1 to 0. Let's do just one more example, just to make sure that we're happy with this. And so go ahead and figure out, what is exp inverse of e cubed? Again, by definition, this is asking us to find the unique A so that exp of A is equal to e cubed. Right? I'm trying to solve fill in the blank, exp of what is e cubed. Or in other words, I'm trying to solve the equation e to the A equals e cubed. Now, I hope this isn't too mysterious. The A here is 3. The power I have to raise e to in order to get e cubed is the third power. So exp of 3 is e cubed, so exp inverse of e cubed is 3. And again, the reason why exp inverse of e cubed is 3 is because exp of 3 is e cubed. All the inverse is doing is swapping the inputs and outputs. So here I had an input of 3 and an output of e cubed, whereas here it's exactly the opposite. I have an input of e cubed and an output of 3. Now, at this point, you might have guessed what this function exp inverse is. Namely, exp inverse is exactly the function we call natural log. If you think back to what natural log did, well, the way I describe it to calculus students is that natural log answers the question, what power do I have to raise e to in order to get this thing? So if I asked for the natural log of e cubed, I'd be saying exactly the same question we were just asking, which is to say I'd be asking, what power do I have to raise e to in order to get e cubed? It's exactly the same function. Now, people quite often have a hard time remembering what the domain of natural log is. But in fact, you see here why the domain of natural log is the positive real numbers, and that's because it reversed the domain and codomain of exp. Now, I do want to note that being inverse functions is mutual. So I could say this more symmetrically as the statement exp from r to r plus and natural log from r plus to r are inverse functions. Now, as a brief aside, this fact that e to the x and the natural log of x are inverse functions has actually impacted your life in a subtle way that you probably haven't realized. Namely, long ago when you were buying calculus textbooks, or were given calculus textbooks in high school or whatever, you had a title of your calculus book that said something that was either something akin to early transcendentals or late transcendentals. And probably some professor or something made some deal about making sure that you got the right one of these two. So what's the difference between early transcendentals and late transcendentals? Well, the difference is, it turns out, which function you introduce first. In early transcendentals, you introduce the function exp first. And then, after you've introduced the function exp, then you define natural log to be its inverse. This is by far the most common, in my experience, of preferences for people who are teaching this class. So this is probably what you saw. In fact, probably you saw e to the x in pre-calculus somewhere, maybe as part of this PERT formula, and probably as examples early on in derivatives, where you talked about how the derivative of e to the x is e to the x, and so on. Certainly any of your calculus classes at Luther certainly fall in this category. So what is late transcendentals then? Late transcendentals, you actually start with natural log first. And then, having defined natural log, you then define exp to be the inverse of natural log. So, why on earth would you prefer this to this? So there are a few answers here, but a lot of them hang on the fact that if you introduce e first, it feels really weird. And so this definitely happens when you're taking pre-calculus and calculus 1 and all of these things, and people talk about the function e to the x, and it feels really weird that you could be talking about 10 to the x, or the log base 10, or you could be talking about 2 to the x, or some other reasonable one, but instead mathematicians, for whatever weird reason, seem to prefer the exponential with this transcendental base that you're never going to be able to really do any by hand calculations with, because it's some ugly 2.7182 blah 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 irrational number. So that is a reason why you might prefer not to introduce e to the x earlier. But you might then say, well, hold on, how on earth is starting with natural log any better? And so the idea is, if you wait long enough, you can actually write down a definition of natural log that is actually relatively nice looking and seems maybe kind of vaguely natural. And so in this definition, if I take the natural log of some input, I'll call that input m, and you could define this to be the area under the curve y equals 1 over x from x equals 1 to x equals m. So if you picture your favorite curve, 1 over x, take 1 here, take m over here, and then it's this area. And so if you think about that, what that's really saying is that log of m is, under this view, being defined to be equal to the integral from 1 to m of 1 over t dt. Now, you might say, well, why is that natural? And so here's a couple reasons why this might, to a certain aesthetic, feel more natural. So one reason is I did not define any strange transcendental numbers in order to write down this definition. I just looked at the relatively reasonable looking function 1 over x, and then I talked about the area under it. Now, you might be inclined to ask then, well, sure, but I could take the area under any function. Why am I taking the area under 1 over x? And so the reason why this shows up very naturally in a calculus course is that this function is part of the power rule for integration. Namely, when you write down the formula for, okay, if I want to take the integral of x to the n dx, that is, and so x to the n plus 1 over n plus 1 plus c, except this formula annoyingly does not work for exactly one n. Namely, this formula explodes for n equals minus 1. When you integrate x to the minus 1, you're forced to confront this function, because this is the function which is the antiderivative of 1 over x. And so that's the idea of late transcendentals, is to postpone talking about e and e to the x, and maybe other exponential functions too, until you get all the way to the end of your discussion of integration, at which point you realize, hey, I need to write down antiderivatives of at least the powers of x. And then, hey, there's this one power of x to the minus 1 specifically, where when I integrate it, something falls out I've never seen before. Namely, this function that I'm going to call the natural log. And then, once you've said that, then you say, oh, hey, well, this function's kind of cool. I wonder what its inverse is. And then you define that function to be exp, and then you do and derive everything exactly backwards of the way that you're probably used to thinking about it. Now, if I were to disclose my personal view on this, yes, I think this makes a much better story. Nothing comes out of nowhere. You can really argue, why is it you always have to think about this function and this number e, and you're sort of doomed that it's going to come up no matter how weird you think it is and how weird it is when you first see it, it's going to come up because eventually you're going to want to be able to integrate x to the minus 1, and you're just not going to be able to do it without encountering something that's closely related to this number e. But this is also a terrible way, in my opinion, to teach people because, well, the number e is important and shows up in all kinds of places like accounting and in this formula for compound interest and in differential equations and in all of these other places. And so making people wait to even think about the number e and the function e to the x until they've already made it most of the way through the calculus sequence seems wrong. In particular, if you do it this way, then you don't get that really nice the derivative of e to the x is e to the x thing when you're in calculus 1. And so anyway, I think it's far better to do it the other way from a student friendliness and learning point of view. But the fact is, definitions are ours to make, and so we can make exactly the same rules of calculus by defining natural log in terms of integration, or defining e to the x in terms of, well, it's actually a good question that I didn't really answer here, which is, if you take the early Transcendentals route, how do you exactly define e to the x? And that also ends up bothering mathematicians, because basically the answer is you just don't and hope no one asks. You just say, oh, well, e is this 2.718 number, and then I'm just going to raise it to a power, and then you sort of pretend that makes sense and go on from there. If you want to really formally define e to the x, well, then actually the best way to define e to the x, or exp if you prefer, is by defining its Taylor series, which then is even further in calculus, and so maybe in some certain senses actually natural log you can really define earlier. Anyway, this is all pretty moot, but I just wanted to give you this sort of glimpse into these two functions being inverses and how that ends up really having deep ripples through all of the math that you've learned in the way it's organized. Now, there's a few more examples, just from your regular experience, that you might be able to identify as inverse functions. So, for example, you might guess that this function we call inverse tangent is actually the inverse of the function we call tangent. And that's almost true. It's certainly true as long as you agree to only define tangent on the interval from minus pi over 2 to pi over 2, as I alluded to when I talked about defining the trig functions earlier. Namely, if I look at tangent only on this interval, then it is a bijection between the real numbers and this open interval. And so then inverse tangent, what is it? It's just the inverse function. It goes the other direction. And so if someone says, hey, what's the inverse tangent of 1? Well, then they're really asking, if I take the tangent of something and I get 1, what is it? And so you might have to think through your unit circle for a bit, but you'll eventually come up with the fact that the answer is pi over 4. And so the inverse tangent of 1 is pi over 4. Now, when you learned about inverse tangent, you might have even thought about the fact that this isn't even the only angle whose tangent is 1. And so, in fact, it's also true that the tangent of 5 pi over 4 is 1. And this is also on your unit circle. And so very rightly, the first and second and third time you talk about this, you're inclined to say, wait, isn't the inverse tangent of 1 also 5 pi over 4? But this can't at all be the case, because pi over 4 and 5 pi over 4 are not the same thing. And so the whole thing I want is I want this to be a function. And if I want this thing to be a function, that means I'm only allowed to choose one value. And the way we arrange to only choose one value is by finding an interval, or what we'll call a restricted domain, where the function becomes a bijection. And so in this case, that interval is minus pi over 2 to pi over 2. And so why can arctangent never give me back 5 pi over 4? It's because 5 pi over 4 isn't in this interval. Now, in fact, this whole idea of the things that are kind of inverse functions that we think about on a day-to-day basis aren't really the inverses of the functions we think they are, this is actually something that comes up over and over again. So here's another example. And this example has to do with the function x squared. What is the inverse of this going to be? Well, I'm going to be saying, okay, if I'm looking for f inverse of b, that's going to be the a, so that f of a is equal to b. So that's going to be the a, so that a squared is equal to b. So really, f inverse is going to be wanting to answer the question, what do I have to square to get b? Which is to say this inverse is really the square root of b. So even square roots, which are something you've probably been thinking about for a long time, are really a form of inverse function. But if I hadn't talked so fast, you might have noticed square root is not the inverse of this function. Why is square root not the inverse of this function? This function's not a bijection. In fact, actually, the first example we did of 1-to-1 was to show this function's not 1-to-1, and the first example we did of 1-to was to show that this function's not a 1-to. So in fact, it's neither thing we want. So what do I have to do in order to make this function a bijection so that square root can be the inverse function of it? I have to change both the domain and codomain. So I'm going to call this f sub mod for this is my modified version of f. In order to make this 1-to-1, I need to take into account the fact that positives and negatives square to be the same thing. And so I can't have both positives and negatives. And so I want to change my domain here to only include positive numbers and 0. In order to make it onto, I need to only include the outputs that are squares of something. And so which real numbers are squares of something? As it happens, that's also the non-negative real numbers. Now note, even though I got the same answer in both of these cases, it's for very different reasons. This greater than or equal to 0 was really a choice I made so that no two inputs in this domain map to the same output under x squared. And this one is, in fact, just replacing this r with the image of the function x maps to x squared. But here's what square root really is. Square root is really the inverse function of f mod. Okay, and I want to stress, this is the definition of square root. Now, again, I want to tell you that the fact that this function written this way doesn't have an inverse is actually something that underlies a lot of the confusion you likely had in early algebra classes. In fact, this probably came up in a lot of guises. So one of them is, you want to solve the equation x squared equals 9. And so you kind of just have to remember that I can't just take the square root of both sides. And if I just take the square root of both sides, I'd say x equals 3, but then I'm missing a solution. Now, what you're trying to do is right. You're trying to say, okay, x squared equals 9. I just want to take the inverse function of x squared to undo it to give me the input that makes this work. But there's actually two of them, so square root, if I tried to give back both of them, wouldn't be a function. And so you learn this sort of crazy trick, or rule, or whatever, that when you take the square root of both sides, you just sort of throw in a plus or minus on the other side, and so then you get plus or minus 3. So this plus or minus that shows up over here in this rule is entirely because of this weird deficiency of the function x to x squared, where it fails to be a bijection like you would hope it would be. You'll notice none of that happens with cubes and cube roots, and that's because x to x cubed actually is a bijection. And so all of these weird eccentricities just don't show up at all. Another thing where this shows up is then, okay, so someone asks you what the square root of 4 is, and after you've learned this rule, it's really tempting to say, okay, the square root of 4 is plus or minus 2. But again, that's not right either, because I want square root to be a function. And so you have to learn that, okay, square root of 4 is always the positive one, but then even people will say things like, 4 has 2 square roots, plus 2 and minus 2, and so that just makes this even more complicated. And so now you're really holding in your head sort of two ideas at once. And those ideas you're really holding in your head are the idea of this natural function that goes from the reals to the reals and just squares a number. And the shadow version of this function down here, where I've stripped away all the negative numbers and refused to think about them, and I really get an inverse function. And so all these sort of weird confusions that pop up around squaring and solving squared equations and all these sorts of things, these are all really inevitable consequences of the fact that this function, nice though it is not a bijection. One last form that this shows up in is the form that we mentioned a few videos ago, which is what happens if you take the square root of x squared. If x squared were a bijection, then the square root of x squared would be x. But it's not. Remember, we said this last time, the square root of x squared is actually the absolute value of x, not x. And again, that's just another way of looking at the fact that this function x to x squared is not a bijection. Okay, so last on our continued story of classic inverse functions that aren't really inverse functions, let's talk about sine and cosine, which if you recall thinking about arcsine and arccosine, had this really weird thing in them where arcsine is supposed to be like something between minus pi over 2 and pi over 2, but arccosine is supposed to be something between 0 and pi, and you were supposed to remember this, and inevitably it led to confusion, and it seemed really arbitrary, and is one of those moments where it sort of feels like, as you're listening to it, that someone is just like making up math on the spot. But again, just like with the square root, actually, the fact that arcsine and arccosine are weird falls out of the fact that these functions, as stated, do not actually have inverses. Why don't they have inverses? Well, they're very much not bijections. Indeed, just like x squared, sine and cosine are neither one-to-one nor onto. And so they're as far from being bijections as possible. So in order to make them bijections, so that we can actually say these things really are inverse functions of something, I have to modify them. And so again, I have to change both the domain and the codomain. One of those is actually fairly straightforward. Namely, the codomain I need to make the closed interval from -1 to 1. In all instances, all I'm doing is replacing the codomain with the image, because I want the function to be onto, and remember, a function's only onto if its codomain and its image are the same thing. The real problem is when it comes to being 1-to-1. Even if I just look at one sine wave, it's already not 1-to-1. And I see that, actually, by looking at some particular output here, and seeing that that output occurs at that input, but that output also occurs at this input. And so if you've talked about one-to-oneness before in like some pre-calculus class, or maybe sometimes it comes up in Calculus 2 or whatever, probably you've talked about the horizontal line test, and the horizontal line test tells you whether a function is actually 1-to-1 or not. So what do we have to do in order to make this function 1-to-1? I actually have to modify this graph so that it passes the horizontal line test. And when I say modify, how am I going to modify it? I'm just going to chop a bunch of the graph off. Now, how exactly am I going to do this? Well, there's a few different reasonable things I could choose. But what we actually do for trig functions is we sort of start at 0, and then I keep going along the graph until I start to repeat. And that actually happens right at this point. If I go past the peak here, then I start repeating output values as soon as I go past here. So in fact, actually, I chop off the graph here at what works out to be pi/2. And so I just remove that part of the graph. Now that's all well and good, but it turns out that this function will not be onto if I just start at 0. And that's because once I chop off all the inputs over here, I've actually chopped off all the inputs that give me a negative output. Unless I rewind backwards, because sine actually winds both directions. And so I'm actually going to also grab this part of the graph. And I'm going to grab it up until this other point, this min, where if I passed that, I would actually start repeating outputs as well. And so I'm going to remove that. So I've removed this piece, and I've removed that piece. And I'm only left now with the interval from -pi/2 to pi/2. And yes, just to make this even more annoying for students who are trying to learn this, it really is the case that the way I modified tangent really had to be an open interval from -pi/2 to pi/2, but the way I modify sine really has to be a closed interval from -pi/2 to pi/2. And that's because tangent is actually undefined at -pi/2 and pi/2 because there's the vertical asymptotes there, whereas sine actually is just -1 and 1 there, so I need to include those. But once you agree that, hey, this is my modified version of sine, this really is a bijection, and so inverse sine then by definition is really the inverse not of sine, but of this modified sine. So here's the part where this really ends up giving people nightmares. What do I need to do to modify cosine? And so your first guess would very naturally be, okay, we'll change the interval to -pi/2 to pi/2. But we have a problem, which is that if I graph cosine from -pi/2 to pi/2, it looks like this. And that is very much not a bijection. And so actually, when I look at the graph of cosine, I actually immediately have to remove all of the negative inputs. But I actually can't stop at pi/2 because remember, I haven't yet gotten the negative outputs. And so I actually have to continue downward until I get to here. And then I can remove the rest of it. And so this is the input 0, this is the input pi, and so in order to make cosine into a bijection, I need to restrict the input to be from 0 to pi, and then going from -1. to 1. And then, once I've done that, arc cosine is actually the inverse function of this modified cosine. So, if you remember having to deal with the fact that I basically needed to memorize this list of sine goes with minus pi over 2 to pi over 2, cosine goes with 0 to pi, and tangent goes with minus pi over 2 to pi over 2, but with parentheses instead of brackets. This is the heart of why that came up. And it's a really fundamentally unresolvable problem. It's just going to be a little bit ugly because of the way sine and cosine work. There's no better way to do it. That's not to be confused with saying there's no other way to do it, just that I think the other ways are not better and often are worse. So these are the choices we've made, and once you sort of understand what the problem is, and understand that in order to make an inverse function, I really have to write down a bijection, you're sort of boxed in almost to making the exact same choices that mathematicians have made. And then this kind of makes sense. Let me give you a couple more examples where we're going to just compute the inverse of something. And so this first one I'm going to give you, the function's just going to be x squared, but I'm going to futz with the domain and codomain a bit. I think you can write down a proof that this function's a bijection. What's its inverse? Now, it would be natural, given that we talked about how the inverse function of x squared is square root of x earlier, to just say, okay, the inverse function is going to be x goes to square root of x. Done. That's not going to be the case, though. And I know immediately that can't be the case, because what are the domain and codomain of f inverse? Well, the domain is r plus, and the codomain is r minus. And so in particular, the square root of something is never in r minus, so that can't be the right answer. So let's try and calculate, say, f inverse of 4. And let's make sure we understand what this is for this particular weird function, and then we'll be able to guess, I think, what the correct inverse function here is. So what is f inverse of 4 supposed to be? It's supposed to be the solution to the equation f of a equals 4. So it's supposed to be the solution to the equation a squared equals 4. Now, again, it really looks like I'm supposed to say a equals 2. But remember, a here has to be in the domain of the original function. So my a can't be 2, because 2's not in the domain. So what is a? Well, there's only one choice. It has to be minus 2. In fact, actually, if I think about it, what this function is always doing is taking b not to the square root of b, but to minus the square root of b. Square root of b is always positive, and I want to be sending it to a negative number. Namely, I want to be sending it to the other square root of b. And the other square root of b happens to be minus the square root of b. And so my inverse function actually ends up being that. So what really just happened here amounts to that we restricted the domain of x squared differently. So normally when we restrict the domain of x squared, as we did earlier, we say, okay, I'm just going to chop off the negative inputs and the negative outputs and be left with just this function from r greater than or equal to 0 to r greater than or equal to 0. Here, though, instead of chopping off the negative inputs, we chopped off the positive inputs. And so we got an inverse to this weird x squared. And so the inverse, instead of always giving us the positive square root, as happened when we removed this piece of the domain, always gives us the negative square root because we removed the positive half of the domain. Here's another function that we proved was a bijection earlier. It was a fairly involved proof, but we did get that this function was indeed really a bijection between r cross r and r cross r. So what I want us to do now is to calculate the inverse function of this. Okay, and so let's write down the definition first. What is f inverse of ab? It's going to be the xy such that f of xy equals a comma b. So to find the inverse, what we're really doing here is solving this equation. And so you might remember, if you've talked about finding inverse functions of things before, that they probably told you something like swap the x and y and solve for x, or something of that sort. That's really what we're doing here, except I don't need to swap the variable names. So what am I doing? I'm solving the equation 2x minus y, comma x minus 2y equals a comma b. Okay, so that is to say I'm solving the system of equations 2x minus y equals a, x minus 2y equals b. And so I will subtract twice the second equation from the first equation, which will give me 3y equals a minus 2b. Likewise, I'll subtract twice the first equation from the second equation, which will give me minus 3x is equal to, those parts cancel, b minus 2a. So that will give me y is equal to a minus 2b over 3, and this will give me x equals 2a minus b over 3. And so what's my conclusion here? My conclusion here is that f inverse of a comma b is that ordered pair. Now, if you have a good memory, you might remember that we did almost exactly this calculation when we were proving that this function was onto, which was part of proving that it was a bijection. Now, at the time, I stressed how solving this equation was logically backwards. But this time it's actually logically forwards, because we know this function's a bijection now, and so I know that this equation has a unique solution, and so I write it down and we just solve it exactly how we did last time, and then that gives us the inverse function. The last big topic I want to talk about today is function composition. And that's where we did this f of g or f of g of x or whatever, that kind of business. And I'm actually going to start by thinking about composing a function and its inverse, and then branch out from there and think about how function composition is going to work more generally. Okay, so we've got a function f from a to b that's a bijection. And so it has an inverse, f inverse from b to a. And I'm going to go ahead and have a little a in a and a little b in b. And I'm going to take f of f inverse of something. And I am going to take f inverse of f of something. And so, first question, which do I put here, a or b? And the answer is I have to put b here, because f inverse takes inputs in b. So this is going to be of little b. Likewise, here, f takes inputs in a, so I'm going to have to put a little a here. So I want to think through what each of these things actually is. So what's f of f inverse of b? Well, you're probably going to guess, and you'll be correct, that it is b. And likewise, f inverse of f of a is a. So why is f of f inverse of b, b? And the key to understanding this is to remember what f inverse of b is. By definition, f inverse of b is the a in a such that f of a is b. And so if I plug that thing, remember this whole f inverse of b is that a, such that f of a equals b. If I plug that into f, well, I'd better get b. And so this is almost a tautology. This is just something that follows from chasing the definition. Over here, when I look at f inverse of f of a, so again, what is f inverse of something? It's asking what I'd have to put in the function to get that output. And so this is asking, what would I have to put into the function f in order to get f of a. In other words, what would I have to put into the function f to get out of the function f what I get out of the function f when I put in a? And though that sentence is difficult to understand and may hurt your head a bit, once you understand what it's saying, the answer is, well, a, of course. And so what I'm saying here is that if you actually combine the functions f and f inverse like this, you get a function, and now that function takes an input in b, but it also gives an output in b. Why does it also give an output in b? Because I'm getting the output from f, and f gives me an output in b. And what does it do? Well, it takes b to b. Right? It is a not very exciting function from b to b. F inverse of f is almost exactly the same, except instead of going from b to b, it actually goes from a to a. But it also is the function that takes little a to little a. So, in fact, when you compose a function in its inverse, you get an identity function. That is a function that sends the input to itself. This is a useful theorem, actually, that we're not going to use probably in this course, but that you may see come up in other courses. And what this theorem tells you is that if you have a pair of functions, then in order to check that they're inverse functions, all you have to check is that if you compose them in both directions, you get the thing we just showed that you always get when you compose inverse functions. So, namely, you get the function that takes little b to little b when you compose f with g, and you get the function that takes little a to little a when you compose g with f. In particular, one reason why this is useful, and probably the main reason why it comes up at least in other courses that I teach, is that this gives you an alternative way to prove that a function is a bijection. Because nowhere in here did I assume anything about a function being a bijection. And so, in fact, as soon as you can write down an inverse function for a function, then you know that function is a bijection. So, in particular, this theorem gives us a way to show a function is a bijection without showing it's one-to-one and one-to. And so basically, just to summarize, what's the idea? Well, only bijections have inverses. And so basically, the idea of this is to say, well, if you can show a function has an inverse, that tells you it's a bijection. It's the contrapositive of what we've been doing for the majority of today. So last up, I want to talk about function composition in more generality. And so when I say more generality, what do I mean? I mean, I'm going to have a function f from a to b, and a function g from b to c, and I'm going to ask, which makes sense? F of g or g of f? And it's not the case that both make sense. And the answer is g of f is the one that makes sense. And how do I know that? And the answer is, well, I think about what goes in here. Namely, some little a in a is what goes into f. And then what comes out is some little b in b, right? I input something in a to f, and then I output the thing in b, and then I put the thing in b into g, which g likes because g takes in things in b, and it gives me out something in c. And so, in fact, g of f is a function that in fact actually goes from a to c. So why does f of g not make sense? F of g does not make sense because if I think about it, what would I be putting in to g? Well, I would be putting in some element of b and getting out some element of c, and so then I would be looking at f of c, except f does not know what to do with an element of c. Elements of c are not what f takes as inputs. So this does not actually make sense. So if I want to go from a to b to c, basically leapfrogging along, and my a to b function is called f, and my b to c function is called g, then the way I do that is to write down the function g of f, not the function f of g. Now, that may be seeming very backwards to you. And here's the reason why. We read from left to right. But when I look at a function composition, like g of f, it's actually read from right to left. Namely, if I have the function g of f, or even h of g of f of z or whatever, however many functions you want, I'm always reading them from the right to the left. And that's because really I'm reading them from the inside out. And so that ends up meaning that I read them from right to left. And so when you want to do a bunch of functions to something in order, you need to remember that that order is going to be written right to left, not left to right. Now, as a last note, I want to note that some people find this so upsetting that they go to really bizarre lengths to avoid having function composition be written from right to left. Here are two of the things that you will sometimes see people do. One is to, instead of writing function composition on the left, write it on the right. So instead of writing that, like we would normally do, write that. And so now when I read this, although it hurts my brain at first, because I do not like this, but when I read this, now I actually do apply g to x first, and then I apply f, so I really do read from left to right, like I'm used to. Or sometimes people will just outright define f of g to mean the opposite order. So they'll just write their function composition backwards so that you apply it in left to right order instead of right to left order. Ultimately, though, no one of these ways of doing this avoids having some counterintuitive / slightly annoying problem. Just like with the inverse functions earlier, all you can do is push the sand around. Somewhere, there's going to be something that's annoying and counterintuitive, and you can make whatever convention you want, but you're never going to truly be able to avoid it, because the thing that's making it counterintuitive is an innate part of the way the math is written. I'll wrap up there for today. In the next video, I'll go ahead and talk about writing proofs with functions. So we'll talk about proving things about functions and proving things with the definitions of one-to-one and one-to, things beyond just this function is one-to-one or this function is on-to, proving things like if this function is one-to-one, then blah, blah, blah. So we'll talk about that again next time. But that's all for now. I'll see you then.